In this video, we're continuing our discussion of spanning sets, linear combinations, and linear dependence and independence. And we're specifically going to look at the definition of linear independence in this video. Consider a set of vectors, v1 through vk, and the vector equation given by this, c1 v1 plus c2 v2, so adding them all up in some linear combination, but suppose it's set equal to 0. This is an equation that you may want to solve, and it always has a trivial solution. By trivial solution, I mean if you just take all of the scalars to be equal to 0, then you're going to have 0 plus 0 plus 0 plus 0, these 0 vectors all adding up to give you the 0 vector. So you can always do that. But can you find some sort of non-trivial solution where the scalars aren't all 0 and the vectors are non-zero as well? Supposing you have such a non-trivial solution, then some scalar has to be non-zero. So let's just say that that scalar is ck. It's the kth one that's not 0. If you have that, then you can use that to solve for vk in terms of the other vectors. When you do that, what you would do is subtract ck vk from both sides of the equation, and then you would divide out by ck, and that would leave you with an expression looking like this. Vk could be written as the sum of ci vi's, and then scalar multiplied through by 1 over ck. But what that means is that vk is explicitly a linear combination of the other vectors, and vk is in fact in the span of the other vectors. When this happens, what we say is that our original set of vectors, v1 through vk, was linearly dependent, the original set S. It has to be dependent because we were able to write one of them as a linear combination of the others. If you couldn't have done that, we would have said that the set of vectors was linearly independent. So we've been talking about linear independence and dependence a lot in passing. We've been using it implicitly or explicitly here and there, but now we're actually prepared to write down the definition of linear independence. So here's the definition that we want. We're going to say that a set of vectors, S, in a vector space, be it Rn or anything else, is linearly independent when the vector equation, c1 v1 through ck vk equal to the 0 vector, only has the trivial solution. Otherwise, if there's any other non-trivial solution, then the set is linearly dependent for the reason that we just explained above. If there's any other trivial solution, you can use it to write one of the vectors in terms of the other vectors, making the existence of a dependence in that set. So this is going to be our definition of linear independence. So as a real quick example, take the vectors 3, 6, and 1, 2. I'm writing them here in coordinate notation, but these are two vectors in R2. These are linearly dependent. It should be clear that one is a scalar multiple of the other. Of course, you can take 1, 2 and multiply through by 3 to get 3, 6. But in the language of what we have used just now, we can write the linear combination of 3, 6 minus 3 as a scalar times the vector 1, 2, giving us 0, 0. This is the non-trivial solution to the vector equation by setting the scalars to be 1 and minus 3. As another example, we have 3 vectors that are linearly dependent in R3. So take, for example, now 1, 0, 1, 0, 1, 0, and 1, 1, 1. Now I can notice just by spot checking that if I add the first 2 vectors together, I'm going to get the third vector. So if I see that vector 1 plus vector 2 is equal to vector 3, then equivalently I could say vector 1 plus vector 2 minus vector 3 is equal to the 0 vector. That's what's written here. So this is my linear dependence relation in either form. The non-trivial solution to the vector equation is taking the scalars to be 1, 1, and minus 1. Because of this non-trivial solution, I have that these vectors are dependent. When you are dealing with vectors in Rn, you can test. The test for linear dependence when you're in Rn is to put those vectors as the columns of a matrix and apply Gaussian elimination. Now, it doesn't matter if the matrix that we produce when we do this is square or not. We can still use this test. Let's take, for example, the 4 vectors 1, 0, 2, 1, 0, 1, 0, 1, 0, minus 1, 0, 0, and 0, 0, 0, 1. Are these independent? Well, in this example, they are going to assemble into a square matrix, but it doesn't matter that they do. So let's go through this. The first couple of row operations that I would do on the matrix that looks like having all 4 of these vectors as its column will be to take the first entry, which is 1, and use it to eliminate the 2 and the 1 that are underneath it. So I'm going to do these elimination steps. In particular, minus 2 row 1 plus row 3 and minus row 1 plus row 4. After that, I'm going to do minus 2 row 2 plus row 4 into row 4. That will eliminate this one. And after that, what I'd like to do is actually a little bit of a row exchange. So I see a row of all zeros here, and I see a row with non-zero entries here, so I'm going to flip-flop them. And at that point, I see that my row of zeros is at the bottom, and I have a nice echelon that's formed. I do not have to continue with elimination in order to see that these vectors are dependent, even though there's more elimination steps that I could do. Because I have a row of zeros at the bottom, I can already see that this 4 by 4 matrix is going to have determinant 0. I can also see with this row echelon form that my first 3 vectors are going to be independent, and that it's the 4th vector that is dependent on the first 3. So I would call these first 3 vectors pivot vectors. That's kind of the terminology for this. These are pivot columns or pivot vectors, and they are all independent. They cannot be written as linear combinations of each other. But the 4th vector can be written as a linear combination of the previous vectors. So this is a dependent column here in column 4. And I know this without having to go further, but I'm going to do one more step in the elimination procedure because doing that step will make it easier for me to see what the precise linear combination that relates them is. Okay, before I had an entry above the diagonal that was non-zero. And in this last step, row 3 plus row 2, that converts it into a 0. So what I've highlighted in pink are the zeros above and below the diagonal. And then I have this last column. And from here I can really read off the dependency relation. So here I can see explicitly that column 4 is equal to 0 times column 1. Column 1 doesn't factor into it at all. Plus 1 times column 2, plus 1 times column 3. So this is written here where I have 4 as a linear combination of the other 3, but I can also see the non-trivial solution to the vector equation that went into the definition of linear dependence. By rewriting this, I can equivalently see that the 0 vector can be expressed as 0 times column 1 plus 1 times column 2 plus 1 times column 3. I don't have a lot of space to do this with, and then minus 1 times column 4. So I see this non-trivial solution to the homogeneous equation as 0, 1, 1, minus 1. So in general, this is going to be the procedure that you use. If you want to see that a set of vectors in R3 or R5 or R7 or any Rn are linear dependent or linearly independent, you can put them as the columns of a matrix and apply Gaussian elimination because it tells you a lot more than just whether they're independent or not. It reveals the precise relationships between those vectors and how to write one as a linear combination of the others. It also gives you a lot of good information that we'll use later when we describe the 4 fundamental subspaces, which is something that we'll get to in time. Now I'd like to do one more example, which is not in Rn. Well, actually, we're going to be able to encode it so that it is in Rn, but at first glance, it's going to look like a problem that's different. So for this example, let's test a set of vectors, meaning we want to see whether they're independent or not, in the vector space consisting of polynomials of degree at most 2. The set that we're going to be looking at for this example is going to be 3 polynomials, 1 plus x minus 2x squared, which we'll call vector 1, 2 plus 5x minus x squared, which we'll call vector 2, and x plus x squared, which we'll call vector 3. How we are going to handle this is we are going to encode these polynomials as numeric vectors, and then after we do that, we will do the standard procedure. So how you encode them is you just strip off the coefficients. So taking a look at vector 1, for example. Vector 1 has a coefficient in the constant spot. That's 1, and that goes into the first entry of vector 1. The coefficient of x is 1, and that goes into the second entry. And the coefficient of x squared is a -2, and that goes into the third spot. You do the same thing with vector 2, and then vector 3 you must take a little bit of care because vector 3 starts with x plus x squared. There's no constant term. So that means the constant term is actually 0. It's 0 plus x squared. So we have to be sure to put a 0 into the first spot. So you encode each one of these 3 polynomials by writing down the coefficients. And these are still called vectors v1, v2, and v3. And then the idea is you just do Gaussian elimination on the matrix that has that as its column vectors. And it's the same idea. So we would assemble these 3 vectors, v1, v2, v3 here as the columns. And then we do a similar series of row operations. This would be the first 2 row operations that we perform. The next set of row operations is going to be another combination of rows followed by 1/3 row 2. And doing our row operations, we eventually get down to something which is in reduced row echelon form. So I'd like to point out that along in this procedure, when we get to about the middle here, and we've produced this row of zeros along the bottom, and we have something which is upper triangular, we can see here, without going any further, that the first 2 vectors are independent, but that the third vector is going to be dependent on the previous 2. And then we keep pushing it further because it's good to have more information, and it's good to see what that exact linear combination is. So at the end of this, I see that I have a pivot column and a pivot column. So in particular, these columns are independent. They're independent of each other. But this third column is dependent on the other 2. And the exact linear combination that relates them is that -2/3 column 1 plus 1/3 column 2 is equal to column 3. That's the linear dependency relation. There's various ways of rewriting this dependency that you see in the matrix. We have it written here in terms of what is column 3 in terms of column 1 and column 2. And if we take that, we can then write the linear combination of v1, v2, and v3 that gives us the 0 vector. This is the definition of linear dependence, that there is a non-trivial combination of these 3 vectors giving you the 0 vector that tells you that they are a linearly dependent set. And by the way, you can also see this if you want to write them back as polynomials. In terms of polynomials, you would just re-encode them with the coefficients in front of the x's and the x squareds and as the constants. And you could see that the polynomials will be added together in such a way as to give you the 0 polynomial. So let's now look at one last example coming from the vector space of 2 by 2 matrices. And we're going to look at a set of 3 vectors and ask whether this set is linearly independent. So I have 3 2 by 2 matrices written here in my set S, and I'm going to call these the vectors v1, v2, and v3. So no matter what vector space you're dealing with, what you're looking for is a solution to the vector equation, the homogeneous vector equation where you have added up v1, v2, and v3, and you're looking for a combination that gives the 0 vector. So as I look for that, I'm considering an equation c1v1 plus c2v2 plus c3v3 and asking when is this equal to, in this case, the 2 by 2 matrix of all zeros, because this is what is the 0 vector in this space. And I am trying to find those scalars, c1, c2, and c3. Well, if I unpack this equation a little bit, then I can see that I've really got 4 equations simultaneously. I have an equation for the first entry of these matrices, the second, the third, and the fourth. And I can try and color code them a little bit. So let me take, for example, the first entry. I want to know whether c1 times 2 plus c2 times 3 plus c3 times 1 is equal to 0. At the same time as c1 times 0 plus c2 times 0 plus c3 times 0 is giving me 0. and likewise 2 other equations for each of the 2 entries in the bottom row. So in other words, this all translates into 4 separate equations, one for each entry of these 2 by 2 matrices. I have the blue entries giving me the first equation in my system of equations. The entries in spot 1, 2, which are the green ones, are giving me the second equation. And I have 2 more equations corresponding with the entries in the 2, 2 spot. And then with the entries in the 2, 2 spot here. 2, 1 and 2, 2. So what I should also see is that there's a matrix that goes along with the system of equations, because I know how to deal with systems of equations. What I do when I want to solve those is I strip out their coefficients and put them into a matrix. So if I take, say, the 2, 0, 0, and 0, which are the coefficients in front of C1, I would be placing them here in column 1. If I take the coefficients from C2, then I would be putting them here. And by the way, this should be a C2, not a C1 in this index. And if I take the coefficients from in front of C3, that's what I see showing up in the 3rd column. And another way to look at these entries of this matrix is that they are the entries of the matrices when read in order left to right and down. So for example, in the first matrix, I have 2, 0, 0, 0, and that shows up here. In the second matrix, I have 3, 0, 2, 1, and that shows up here. And 1, 0, 2, 0 shows up here. So I take my information and I just repackage it into a matrix. In this case, I have a 4 by 3 matrix. And I want to ask myself whether the columns of this matrix are linearly independent. And for that, I will use the standard procedure of Gaussian elimination. Gaussian elimination is something that we're becoming well versed in. So here are the steps for that procedure. There's a few of them to do, but after you do them all, what you see is you get a matrix. There are 4 rows and 3 columns in this matrix. One of those rows is definitely going to turn into a row of all zeros. But we don't have any columns that are dependent on the other columns, because in this problem, unlike the previous examples that we looked at, we didn't start with a square matrix. So the existence of that row of zeros at the bottom does not mean that we're going to have a dependent column. There's something special about being a square matrix when you see that, but here we did not have a square matrix. And what I see is that all 3 of these columns are linearly independent. No one of them can be written as a linear combination of the other 2. So this set of 2 by 2 matrices that we were looking at in the vector space of 2 by 2 matrices was indeed a linearly independent set. So to wrap this up, I will just note here that in this example, all 3 columns of this matrix are independent. Therefore, all 3 of these vectors, which are actually matrices that are 2 by 2, but they are vectors in their own vector space, are independent. So the system that we see here, this system star, this system has only the trivial solution, and hence the original vector equation up here that we looked at, this one, this also has only the trivial solution.